Hey, welcome back. Chapter 1, Section 2, displaying quantitative data and graphs. We're going to get right into this. Again, trying to keep these videos under an hour so your attention span doesn't waver. It probably will, but we're rolling anyway. Again, I'm not really going to cover the book notes. You can do this, how to make a dot plot, and make sure you know what symmetric skewed right, skewed left is, and all of these other things. Okay, we're going to dive straight into the class examples where Phoebe and Lisa bought a 12-pack of soda and measured the number of fluid ounces in each can. Here's the data. It says make a dot plot of these data. So let's make a dot plot. Dot plots are easy. Let's go through and make a number line. I really don't need arrows. Okay, and then we got to find our minimum. Our minimum looks like it's this 11.98 number. Oh, no, it's 11.97. All right, and then my maximum looks like it's the 12.12. All right, so I need all mine to go between there. How you scale this is completely up to you. When I did this, I started at 11.95. and then went up by 5. Just give yourself enough room. Don't really put this in close together. Give yourself room. So there's 11.95. There's 12.0. There's 12.05. There's 12.10. And there's going to be 12.15. So there you go. And then all we got to do is start plotting all the points. So 12.01 is going to be there. All right, 1205 is going to be there. 1198, 1212, 1208. And I trust that you can do all of this, so I'm just going to kind of speed through this and show what I have at the end. So mine kind of looked like this. If you need to slow this video down, go for it. Okay, so that's what I got. There's our dot plot. Again, pause if you haven't caught up yet. I know I went kind of fast because I just kind of threw them all out there because I've done this before. But there's our dot plot. Okay, if you wanted to go through and make individual, marks for there's 1201 and 1202 and 1203 and 1204, and I obviously didn't do that very well because it's not evenly spaced, but you totally can. As long as it's easy to read, that's what really matters. Make it easy to read. So there's our dot plot. B says the company claims that its cans contain 12 ounces of soda. Do these data give Phoebe and Lisa reason to doubt that claim? So if Coke or Pepsi or whoever says they have 12 ounces of soda in each can, do we trust them? Or at least, is their claim reasonable? It's not that we have to trust them, but is their claim reasonable? Well, they said they have 12 ounces of soda. So there's our marker on 12. And if we look at it, yeah, that's a very reasonable claim, right? Of the 12 cans that Phoebe and Lisa tested, 10 of them have more than 12 ounces. All right, that's 10 out of 12 that have, satisfied this guideline. So yes, that's reasonable. So to answer the question, though, do these give reason to doubt the claim? No, we don't have reason to doubt the claim. Of the 12 cans, like we just said, of the 12 cans tested, 10 had at least 12 ounces, right? So we're good. Now, if it's getting kind of, the other way around, then yeah, maybe we should doubt this claim, right? But this one seems to be good. All right. So the dot plots display show two different sets of quantitative data. Graph A shows the result of 100 integers. Results of 100 integers from a random digit generator. Oh, so they went from 0 to 9, all 10 digits, and they just randomly generated a number, and that's what A is. B says the number of grams of fiber in one serving of frozen pizza for several different brands. So it just says describe the shape. So we're looking at A, this random generator. What do you think? Think about it for a second before I write it down. I would say you can describe this as kind of two ways. You can either describe this as roughly symmetric, or you can describe it as approximately uniform. Now, notice I'm using the word approximately and or roughly, right? Is it perfectly symmetric? No. Is it perfectly uniform? No. But is it close enough that we can kind of call it that? Yeah. Now, I know on this approximately uniform deal, the ones are a little low, right, to really call this uniform. But if you look at it, right, we kind of have this, like, there's not a whole lot of, yeah, it comes down, but then it kind of, like, there's not a whole lot of, the thing is that there's no clear peak, right? That's the problem, no clear peak. And since there's no clear peak, yes, that does make, I mean, a perfectly uniform graph is also symmetric, right? So there's that. The reason why this is okay is because we do have this little gap in there. That being said, there's only one. It's not crazy if you look at the distance to that one, the next lowest one. It's not terrible. I would describe this as approximately uniform, even with the one column there. Okay. Again, when you describe these, really general, like it's not like, oh well, this one is like two higher than that one, and then, no. Don't get into the weeds. Look at it. This one's pretty close to being flat. A couple dots moved here or there makes this almost exactly flat. So, whatever. Okay, fiber in the pizza. This is very clear. We got one dot here, and then we jump up, and then we kind of come down here. So this one is definitely skewed to the right. Skewed to the right. I've got more data trailing off to the right. That's going to pull that mean to the right. Therefore, this is skewed to the right. Okay, we have a peak at 2. Most pizza have 2 grams of fiber, apparently, which is very good for you. You should definitely eat lots of fiber. Okay, so there's that. How many calories in that slice of pizza? So here's the calorie servings, or calories per serving, for the 16 brands of cheese pizza, along with a dot plot for the data. It says here are the calories. I apparently did not give you the actual data, which you don't really need because you can see it all there on the dot plot, right? That's a 380, that's a 260, so that's a 290, right? That's a 310. You can see all this. You don't need the actual data. So here we go. It says, describe the distribution. When we describe this distribution, what should we be doing? And the answer is socks. Now, when I say socks, the old way was to talk about shape, outliers, center, and spread. Therefore, socks. They've since said, spread's not a very statistical term, so we're going to eliminate the word spread and use the word variability. If I could spell variability, which is a more technical term, but sock just doesn't really ring as good of a bell as socks does. So I'm going to talk about socks, but just know that I mean sock. Right? We're talking about variability. I think if you use the word spread on the AP exam, I don't know if they're going to mark you down or not. I'm pretty sure they're going to know what you mean. At the same time, let's be more statistically accurate with our language and just you say variability. All right, so shape. Let's describe this shape. How do we feel about this shape? I would argue that this shape is approximately symmetric. By the way, the word approximately is almost the only word that I will abbreviate. Okay, everything else we write all the way out. Roughly symmetric or approximately symmetric with peaks at 320 and 340. Okay, I have a peak there, I have a peak there. I know it's not that big of a peak, but this one is only 1, 2, or 3. I got 2 3s, so let's call them out. All right, I do have some gaps, so if we can, we call out gaps. Gaps I called out from 290 to 310. Right, there's that gap there. We also have a 360. Oh, I missed one. I was looking at the other line. All right, we'll cover them all. We also have a, what do I say, a 360 to 380. There's that small gap there. There's also the bigger gap of the 260 to 290. That's the big gap going on right there. I would say when you list your gaps, please list them in order, like I did not. I was kind of reading my notes here and I missed it. So we have it on there, so that's the important part. Yeah, gap, gap, gap. Everything else is right next to each other, right? Is this gap that big? Not really, and that's what we're going to talk about with outliers. There is an outlier test. We will go over that in 1.3. So we don't actually have the outlier test. We cannot say for certain this is an outlier and this is not. The question is here's the bulk of our data right here. All right, we called out this gap and this gap and this gap. The question is are those gaps significant enough to warrant that those are outliers? And I would argue that of the gaps, so this is definitely the smallest one. It's not that bad, or it's not that far out where you're like, wow, that's so much. It's not like 380 is so much. I mean, you got 2 at 360, right? You have 3 at 340. That's not that different, right? So I'm going to say 380, not an outlier. When we look at 290, again, that's only 20 away from 310 there. Again, there's 2 of them there, and then there's 3 of them at 320. So there's a lot of data in comparison to this data set that's not that far away from the 290 mark. So again, that's not actually that. If I say 290, you're not like, wow, because there's 2 310s and 3 320, right? But now when we go to 260, one, that's the biggest gap, but it's followed by another smaller gap before we get into the rest of the data. So a 260 seems a lot lower in comparison to all the 310 and the 320 where the next big bunch of data is, right? So we're going to say possible outlier at 260, right? I say possible because, again, I don't have the outlier test in my back pocket at the moment, so I'm not going to say for sure. Never say for sure something you don't know for sure. You need to be 100% certain to say this is the case, right? So I'm going to say a possible outlier at 260. I'm fairly confident it is an outlier, but again, I don't know for sure. Okay. Now, as you go through this center, you can talk about 2 things, means or medians. Let's talk about the fact that we have an approximately symmetric shape. Therefore, doing a mean is the most appropriate, but I did not want to calculate the mean, so I just found the median. So I'm going to write down the median, and we're going to find the median. It's not that median is bad, but when things are approximately symmetric, you use median. When things are when things are approximately symmetric, you use mean. When things are skewed, you use median. So you just you add all these up, divide by the number, in this case 16. I didn't want to do that. You can just seriously for median, these are all in order, cross out, cross out, cross out, cross out, and just keep going back and forth until you end up at where you need to be at 330. So the median number of calories? Yeah, calories in this is 330. Now, because this is approximately symmetric, the mean should be pretty close to 330 as well. Okay, it will probably be slightly lower because of that possible outlier. Although I will say when things are approximately symmetric, you're supposed to use mean. However, when in the presence of outliers, you are supposed to use median. So maybe median actually is the better case to use here because of that. Okay, so maybe my laziness was actually the right thing to do. Okay, and variability, you can talk about IQR, which is a 1.3 thing. You can talk about standard deviation, which I think is also a 1.3 thing. And so the only thing we really have is the range, right? So I'm just going to say that data varies from 260 to 380. We got a 120 calorie range as we go. Okay, so That sucks. Any assignment says describe the distribution, you are doing socks. Shape, outlier, center, spread. And like I said, the more we go in, the more you actually get the outlier test. Probably you should actually do the outlier test, right? For center, be accurate on mean versus median, and then the appropriate standard deviation versus IQR, which again we'll talk about later in 1.3. Okay. So here we go. Moving on. Next page, page 11. It says how many shoes are too many shoes? How many pairs of shoes does a typical teenager own? To find out, group of statistics students surveyed separate random samples of 20 female students and 20 male students from their large high school. Here are the dot plots of the number of pairs of shoes owned by the survey respondents. Compare the distributions of pairs of shoes for females and males. I will say as a general thing, yeah, you guys probably have way too many shoes. You don't need as many shoes as you think you do. You don't wear them enough to actually justify owning all of those shoes. But, you know, whatever. Okay, so what do? It says compare the distribution. So compare the distribution. So what are we doing? We're doing socks, right? We're doing socks or sock. But when we compare, we have to make sure we do comparison language. Okay, now when we start talking about socks and shape, it's hard to compare shape, right? When I say comparison language, I mean greater than, less than, about the same as, right? That's comparison language. Skewed right is not better than skewed left, which is not approximately the same as approximately symmetric, right? So, like, when it comes to shape and outliers, really, all we're going to do is kind of note, hey, females look like this, males look like that. Outliers, females have this, outliers, males have that, right? When we get to center and spread, that's where we're really going to compare greater than, less than, about the same as kind of deal. So shape. Describe the female shape. I describe the female shape. Females... To be fully accurate, we should write the distribution of females. I didn't give myself enough room to write that, so I'm just going to write females. Is skewed right? All right, peak at, what is that? I wrote 13. Peak at 13. So females is skewed right with a peak at 13. Males is, I'm going to say also skewed right. I'm going to actually use the word also, even though it's not really a comparison word. It kind of feels more comparison-y, so it makes me feel better about the comparison. All right, but I'm going to call out the two peaks, one peak there and one peak there. I'm going to call that 7 and 10, right? Peaks at 7, that makes that look more like 7. 7 and 10. That's my and symbol, by the way. Okay, 7 and 10. All right, so there's my shape. Now let's go to outliers. Again, we're just going to talk about possible outliers. Now, when we talk about possible outliers, where's the bulk of the data for females? Well, our peak is here all the way on the left, right? We got a good cluster of data there. Right? Then we got this huge gap here, which we could have talked about in shape, right? We could have talked about gaps, not as necessary. I mean, they're talking about the whole thing, like shape, outlier, center, spread, skewed right, skewed left, right at peak, call it a day, run off with it. If they just say describe the shape, then you need to be more specific. So, right? So, our peak is here, bulk of data here, gap here. But then we have another grouping of data here before we have our final kind of outlier-ish point. But when you take a look at, like, is that far away from a chunk of data that's going to make it an outlier? And with that chunk right there, I'm going to argue no, right? So I'm going to write, but again, do I know for sure without calculating it? No. So I'm going to write no apparent outlier if I could spell, for females. Although I don't know what you do with like 58 pairs of shoes. Goodness gracious. How many shoes does one need? All right, and then we look at males. Now, males, on the other hand, bulk of my data is here. Holy moly, that's like almost all of it. We got a small gap here with then a 21, let's call it, maybe a 22. And while that could be an outlier, it's attached enough that, maybe not. These two definitely, right? But when they ask for outliers and you're not expected to do the outlier test, the question is, if you're having trouble deciding whether it is or it isn't, call it out as a possible. We have, what's this? If this grouping's 10, that's 11, 12, that's 14. And if that's 21 or 22, we have a gap from 14 to 21 or 22. You know what? That's a big enough gap where I might actually call that one out. So I'm going to say 22. And then I called that one 35 and then 38 as possible outliers. For males. Right? Again, that one's a maybe, but it's far enough away with a big enough of a gap that I'm like, all right, I'll call it. Especially because single point, single point, single point before we get a 4 on top of each other, right? So when we go over the outlier test, you'll start to realize, yeah, that probably is an outlier. Because there's only 20 males in here, that might not actually be, but we'll get the outlier test later and figure it out. Okay, shape, outlier, center. Center. Now, again, these are skewed to the right, which means we should be finding median, right? Mean or median for center, we should be finding median. So, mean is, right, these data points way out here. Outliers or no, it's just skewed to the right. They're going to drag that mean out, so we should not be using mean, right? So, find the median for females. Do your little crossing out trick. 1, 1. 1, 1, 1. You keep going. I want you to pause the video, find the median for both females and males, and then compare them. All right, so when I write this down, I'm going to say the median for females, and then I'm going to give the number. I got a median of 26. Holy moly, that's a lot of shoes. Is greater than the median for males, and I'm going to call that number out, which is 9. Which I think I'm right about there. I got 2 pairs of dress shoes. I got my regular shoes. There's 3. I got a pair of snow boots. There's 4. Got a pair of basketball shoes. There's 5. I have, do we count flip-flops? I count flip-flops. There's 6. I've got 2 different pairs of like little quick slip-on shoes only because my wife bought me another pair even though I didn't think I needed it. So there's 8. I think I have 8 pairs of shoes. There you go. I'm below the median. Who needs that many shoes? All right. Oh, I guess I have a pair of yard work shoes. I got 9 pairs of shoes. There you go. All right, here we go. How many medals? This table represents the number of total medals of 28 countries. Represents the total of medals 28 countries won during the 2016 Olympic Games in Rio de Janeiro. Let's see. The Olympics are coming up in 2024, right? That's soon. They're in Paris. And then after Paris in 2028, they're coming to Los Angeles. They're coming to America, baby. Okay. It says make a stem plot of these data. There's our data. Let's make a stem plot. So, here we go. Stem plots. Draw a big, fatty vertical line. My smallest one is 10. My biggest one is 121. So I'm going to start with a 1, right? And then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? And then when I put my data in here, I have two 10s. So there's a 0 and a 0. So that represents 10, right? The 1 and the 0 represent 10. The 1 and the 0 represent the second 10, right? And then we keep moving on. I've got 1, 2, 3, 4, 5 11s. So I need 1, 2, 3, 4, 5 1s. Got two 13s. So two 13s, two 15s, a 17, three 18s, and two 19s, right? And then when we get into the 20s, I've got a 21, and a 22, and a 28, and a 29. Notice how when I did this, I stacked these up on top of each other, right? That's the goal. So that we can see, if I wrote all of these ones, I spaced these ones out intentionally. If I wrote all these ones, 1, 1, 1, 1, 1, right? But then went 3 and 3, that's just not a good gap, because underneath I gotta fit these so we can see that the length of this stem and leaf, I should say this leaf, this is the stem, these are the leaves, right? Of the stem and leaf plot, even though it's just called a stem plot now. They don't like leaves apparently anymore. The length of this is going to matter. It's easy to see as your eyes look at this, and you can see, oh, that the leaves of that stem, there's a lot more leaves there than there are here. What does that tell you, right? If you space these out more than you space these out, you're going to end up skewing the data unintentionally. We talked about in section 1 about how you want your displays to be as simple as possible to read. Okay? We don't have anybody in the 30s. So we're going to skip it all together. Not even put, don't put a 0 and say there's nothing there, because that looks like it's a 30. Don't do that. Right, I got a 41, a 42, and a 42. Okay, I got a 56. I got a 67. I got a 70, and I got a 121. So there's my stem and leaf plot. One small side note, you can split stem this, so you can go 1 and then 1 and then 2 and then 2, right? And then your 0 to 4s would be here, and your 5 to 9s would be here. And when you have something that big, you know, it might be useful, but I didn't do that because holy crap. And that means when you do it, you got to do it for all of them. So 3, 3, even though there's no 3s, 4, 4, 5, 5, 6, 6, 7, 7. Holy crap, that's going to be way bigger than it needs to be for this, so I didn't do it that way. Okay, if we had 28 data points and all of them were within, 10 to 30, then yeah, we might split stem this, to make it a little more easily readable, rather than having, 3 or 4 stems that are ridiculously long. Let's split those off into shorter ones and see if we can't see more of a pattern. But when we got like, holy moly, like no. Okay. Also, always remember that you need a key. All right. So call out any one individual point. So I'm going to call out 41. So 4-1 is a country that won 41 medals. Okay. Otherwise, is that 41? Is that 4.1? Is that 41,000? Like, I don't know what the scale is unless you tell me, right? 4,100? Like, I don't know, right? You need to tell me. That's 41. 41 what? 41 medals. Always include context. Okay? So there's our stem plot. Then it says describe the shape. How do we describe the shape of the distribution? Okay? This is not full socks, right? It's just describe the shape. So describe the shape. This should be very obvious. Now, stem plots are a little weird because they're vertically oriented instead of horizontally oriented. But just make sure you take this and flip it horizontal with the 1 there and the 12 there as you go. And if you just kind of turn your head to make it so, you should see that this is obviously skewed right. And when you call out a peak at 10 to 19 medals, right? We have a range there, all right there. It's not just here. It was one specific point. We had a peak at 13 or a peak at 10. Here, my peak is at the 10s, all of them. So 10 to 19. Okay. I'm also going to call out, even though outlier is one of those things where it's like you should mention it. Where does it belong? 121 looks like an outlier. Appears to be an outlier. Okay, there you go. When it says make a frequency histogram, remember frequency is totals. Relative frequency is percentage. So how many do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I got 17 metals in the 10. So when I make a histogram, I do this. I need to get up to 17. I started at 0, went up by 2s. 2, 4, 6, 8, 10, 12, 14, 16. That's terrible. I should go up to 18, right? I should go up to 18 because I have 17 and 16 is not enough. I should go up to 18. I ran out of room. Okay. Remember, with histograms, you need to make equal width bars, and these touch each other, unlike bar charts. So I'm going to start with 0 again, and then there's 10 for the sake of order. I'm just going to call out every 20. I'll make a mark for every 10, but only call out every 20. Right? The goal is to make equal length. Oh, that wasn't very equal, huh? Okay. And then draw your bars, right? So between 0 and 10, I have nothing, leave it blank. Between 10 and 20, I have my 17, so go up to 17. I have 17 countries between 10 and 20 medals. Then I have 4 countries between 20 and 30, right? So 4 go up to 4. These touch, so I just do that. Keep in mind, when I say 20 to 30, I don't actually mean 20 to 30. I really mean 20 to 29. Now, the thing about histograms, it is inclusive on the left and exclusive on the right. So while you can't win, 29 and a half medals. So the half doesn't matter for us in this scenario. Theoretically, we can get up to 29.999999. And once we hit 30, we're now here. Right? We don't have any 30s in this one, but that's how that works. So if I have 20, I'm here. If I have 30, I'm here. If I have 29.9999, I'm here. Okay? So that's how that works. All right. I had 0 30s, so again, leave it blank. I had 3 40s, so go up to 3. I had 150, 160, 170. And then my 121 means that I have to go up all the way to 1. Well, I can leave it there, 130. But I'm going to write 140 since I labeled every 20 because I need 1 here. There you go. There is our histogram. All right. Bars touch. It's a frequency, so it's just the number. And then D says what percent of values in the graph are less than 30. Less than 30, so that's all of these. Count them up. How many are there? You should get 21 and a 28, which you should please be able to do without a calculator. What is 21 divided by 28? That's 75%. Okay, 75%. But it says interpret this result in context. Context is going to be the key word over and over and over this year. So context, 75% of the countries won fewer than 30 medals during the 2016 Olympics. Be specific, right? 75% of the countries won fewer than 30 medals during the 2016 Olympics. And there you go. There is your 1.2 notes. Next one is 1.3. So, there you go. You can do the homework now. If you have any questions, please ask. Look, I even made this video under 40 minutes. Look at me go. Chapter 1 is also kind of a shorter, the lessons are shorter. It's stuff hopefully you've seen before. We're probably putting some more specific language and more specific targets on some of these things, but hopefully you've seen some of the stuff where you've seen a dot plot before. Hopefully you can figure out how to make one, and we're just putting some more precise language on how to do that to be specific and the most accurate. Okay, so there you go. There's 1.2. See you around for 1.3. Happy mathing, everybody.